5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to Pluto and then beyond.
Hello. Welcome to the Applied Physics Laboratory here in Laurel, Maryland. Today we're going to be doing a NASA social to do a deep dive into Pluto and NASA's New Horizons mission. We're also joined by our friends who are following online at Lowell Observatory in Flagstaff, Arizona, where Pluto was discovered many, many years ago. For those of you who are joining us online, we're going to be looking at the science, the engineering, and some of the amazing things that New Horizons is going to be doing upcoming for its July 14th flyby of Pluto. If you're following online, the conversation is being done with the hashtag #NASASocial. Starting now, going all the way through the entire Pluto flyby, we're going to be talking about the mission using the hashtag #PlutoFlyby. And if you want to follow along with the mission, you can join us on @NASANewHorizons on Twitter and also on Facebook. Without any further ado, we're going to jump right into it here. First up, to welcome us today from the Applied Physics Laboratory is Mike Ruszkiewicz, the head of space exploration. Mike?
Thanks, Jason. Welcome, everybody. We're very happy to have you here this afternoon at the Johns Hopkins Applied Physics Lab. We're going to hear a lot today about our journey to Pluto and how we got to this point, but I'd like to tell you a little bit about Johns Hopkins Applied Physics Lab journey into space, because it actually begins during the depths of World War II. The lab was actually founded to work on proximity fuses for naval anti-aircraft guns, and that invention was deemed as one of the three most technologically important inventions of World War II, along with the atomic bomb and radar. If you fast forward just a couple of years, James Van Allen, same James Van Allen that, for whom the radiation belts are named, and you'll meet Dr. Jim Green, who's one of his students in a couple of minutes, started using the German V-2s that were brought over here after the war and sounding rockets to begin the exploration of space, leveraging on the electronics, the high-G electronics that they had developed for these anti-aircraft shells, and began the exploration and the understanding of both of near space. If you fast forward a few more years, after the launch of Sputnik, some of the scientists and engineers at the lab were tracking Sputnik and listening to the radio signals from it, and realized that they could actually track the satellite by listening to working on the Doppler shift of the radio signals. And then they had the brainstorm that they could turn that process around. If they were on the ground and could figure out where the satellite was, if they knew where the satellite was, they'd be able to figure out where some point on the ground was, and that led to being able to solve a really critical problem for the Navy and navigation. That really put us into the space business, and I'm not going to go through all of the dozens and dozens of space missions and spacecraft we've launched in between then. I just talk about a few current ones. We do a lot of heliophysics work here, a lot of planetary work here. On the heliophysics side, we're in the full throes of development of our Solar Probe Plus mission. We'll actually be flying through the outer corona of the sun, so you might want to look at that one. We'll be flying within 10 solar radii of the sun to understand how the structure of its magnetic field and how the corona is heated and how coronal mass ejections and the solar wind are generated. A little more closer to home, we've just finished the Messenger mission to Mercury. We had a really wonderfully successful mission, but unfortunately our fuel supply was finite, and we did what we called the splat into the surface of the planet a few weeks ago. And Mercury and Messenger are kind of a little harbinger, because before the Messenger mission, we knew about that much about Mercury. We had seen one side of it from the Mariner mission. The other side of the planet we didn't know anything about. And today you have a high-res version on your screen but we have a complete globe of Mercury and a lot of detailed knowledge, and that's of course just the visual representation, because the scientific discoveries of water ice at the poles and the craters, things like that, are positively mind-boggling. I'm really excited to be here with you. I'm really going to be excited. Hopefully you'll be following us over the next few weeks, because what we're going to learn about Pluto over the next weeks and then months as all the data gets downloaded is really exciting to me. Right now, our canvas for Pluto kind of looks like that, and as we fill that in, it's really going to be amazing. So thank you for being here this afternoon, and thank you for following us and sharing our adventure with the world. Welcome.
Wonderful. To set the mood just a little bit, we've got a quick little video to just kind of introduce Pluto.
There's a mysterious zone far out in our solar system. It's a region of ice worlds, some solitary, some with moons. Their names may be unfamiliar: Eris, Makemake, Haumea, but they hold clues to all our origins. And the first of these worlds, and the one we'll reach in 2015, is the king of the Kuiper Belt, Pluto. The long journey of NASA's New Horizons mission began in 2006 aboard America's biggest, baddest rocket, tricked out with every conceivable booster.
We built a very light spacecraft and bought a very large launch vehicle, and the combination is ferocious.
But in some sense, it all began in 1930 with Clyde Tombaugh, 24 years old and fresh off a farm in Kansas, but willing to spend long hours scanning star fields to find a moving point of light. Humanity's first glimpse of Pluto. The dream of actually getting to Pluto began with a 6-year-old boy in love with science, who grew up to lead a team of brilliant researchers and engineers with dogged persistence through decades of planning and building and testing. A race against time just to get to the launch pad.
Exploring the outer solar system, because it's so far, takes a lot of time. It requires a lot of patience, a lot of dedication, a lot of perseverance, but it's the frontier.
Assuming all goes well at Pluto, NASA may choose to extend the adventure further out into the Kuiper Belt, the solar system's mysterious third zone.
This is maybe the one chance in my lifetime that we're going to get a spacecraft out there and look up close at one of these Kuiper Belt objects.
December 6, 2014. New Horizons wakes up for the last time from hibernation.
New Horizons is speeding towards Pluto at a phenomenal rate, and we can't wait for it to get there.
January 27, 2015, 6 months of approach science begins. July 14, 2015, New Horizons' long journey, 3 billion miles, 9 years in flight, and 85 years of speculation about Pluto, climaxes in one day of close approach and flyby.
You know, we're rounding third base and we're headed home.
The dream, the adventure, the promise of discovery. That's what makes 2015 the year of Pluto.
All right. Some of those faces that you see in there are going to seem really familiar because we're going to hear from them now. Up first to talk with us a little bit about NASA's planetary science and how this mission, New Horizons to Pluto, fits into that is Dr. Jim Green from NASA headquarters. Jim?
Thank you very much, Jason. So this is an exciting time, obviously. Pluto is a beautiful planet. What we call it, we don't care whether it's a dwarf planet. It's a body well worth investigating. It is the archetype of a brand new set of objects. Imagine in your lifetime, we have discovered a whole new region to explore in our solar system, that third zone. What do we mean when we talk about it as the third zone? Our terrestrial planets, Mercury, Venus, Earth, Mars, and even the asteroid belt, you know, that's an area where there are material that was trying to become a planet, but Jupiter wouldn't let it. Gravity kept pulling them apart. And then that second zone, the gas giants, Jupiter, Saturn, Uranus, and Neptune. And now, Pluto is part of maybe 10,000, 20,000, 30,000 objects just like it. For the first time, we're going to fly by Pluto and get a good look. Now, I'm often asked, why are we just flying by it? Well, as Mike mentioned, when he talked about Mercury, we did fly by Mercury once. We do that, those are reconnaissances. Once we see what those bodies are like and we make the plans to go back, then we want to orbit. And then, of course, the next thing is orbiting gives us high-resolution information that allows us then to land, and then rove, and then perhaps return samples. When you look at the moon, we flew by it, we orbited it, we landed, we roved, and we returned samples, our closest object to the Earth. Where are we with Mars? Well, we flew by Mars early on, more than 50 years ago. We orbited it with many orbiters. We have landers down on the surface now and orbiters. And the next step, of course, is we want to be able to bring back samples. So, Pluto, here we come. This is a flyby mission, a historic mission. We want to get a good look at it. That's going to enable us to figure out what those next steps are. And I believe this object is going to be so exciting, we're going to want to get back. And I hope we're able to get back in our lifetimes, perhaps even orbit it. That would be truly a spectacular mission. But right now, we're well on the way. As Alan mentioned earlier in the video, we're, I think, more than in third base. We are moving fast on the way to a home, and it's going to be a real home run for us. So I think with that, I have time for a few more questions if you have any.
All right, for those who are in the room here, if you can wait for a microphone. Otherwise, we've got questions on the line from Lowell, and we're also taking your questions using the hashtag AskNASA if you're following along at home. First question.
If New Horizons proves that there's water on Pluto or inside Pluto, does it make any difference in the status of Pluto?
The stature of Pluto, in my mind as a scientist, is already there. It's already an object well worth examining in great detail. You know, the more we see and analyze the data from our missions, the more we realize the importance water plays, not only in life, but in all our areas in our solar system. And I believe the Kuiper Belt is full of water ice and full of other volatiles, and perhaps played a very important role in seeding life here on Earth. You know, we now know from our models that the planets where they are now, particularly the gas giants, are not in the location where they originally formed, and that Jupiter's gravity pushed them around very early on in the solar system. That took that Kuiper Belt area and brought it inward, brought in the comets, brought in the asteroids, and brought in the Kuiper Belt objects, and brought in water that then, of course, here on Earth is so essential for life to grow. We're just beginning to realize the importance of the Kuiper Belt objects. And so I wouldn't be surprised if we see water ice. I wouldn't be surprised if we see features on it that tell us a lot about how these objects get together, and that's going to be critical for our understanding of the origin and evolution of our solar system.
Wonderful. Our next question comes from Lowell Observatory.
Hi, my name is Carmen Austin, and I'm at the NASA Social at Lowell Observatory. And I have a question about the speed of the New Horizons spacecraft. So I know it's been mentioned today, and we like to say that New Horizons was the fastest spacecraft ever launched. And that sounds awesome. But I've also heard that the Helios 2 probe is the fastest man-made spacecraft or vehicle of any kind ever. So which is really the fastest, and why do we say that both are the fastest? What's the difference?
Well, indeed, as the little video told us, we stripped down the Atlas. We got as much power out of it as we possibly could, and on launch, it indeed was the fastest spacecraft. But you know, as these spacecraft move through our solar system to get where they need to go, there's all sorts of gravity assists. There's all sorts of things that we have to do to change their speed, change their direction, to be able to get to their location. Indeed, Helios 1 and 2 are very fast spacecraft. They are no longer in existence. They no longer have any data to give back. They've been dead for probably 20 years. And so we need to keep looking ahead. And indeed, New Horizons is currently the fastest spacecraft in our currently operating fleet, bar none.
All right.
Thank you very much.
Next question from in the room here. Other questions?
So it's been 9 years since it was launched. What was the planning time frame before that? So what's the whole scale from dream to getting there?
So it took many, many years, but you know, I wasn't involved in the early part of it, but Alan was. And so please hold that question for Alan, because I'm sure he'll tell you how hard it was to go through the process of finally getting this mission on the books. But I will tell you that each and every one of our missions do indeed take a long time to mature the concept, to get it just right, and make it competitive so that NASA then selects that best idea. This is really a tough business from that perspective. But when we do make a selection, you can be guaranteed that these are the top missions that humans have ever put together in these areas. And New Horizons is certainly in that category.
All right, another question from Lowell.
Hi, good afternoon. This is Michael Kaiser from the NASA Social at Lowell. So my question has to do with the spectroscopy instruments on New Horizons. To what extent will we be able to determine the chemical makeup of either Pluto or Pluto's atmosphere or Charon? Thank you.
So that's another really great question for Alan. You know, I don't want to take any of these questions away from him because he's really got the details on all the instruments. So let's save that one for him.
All right, other questions in the room?
Hello, Dr. Green. I'm Tamar Baines. You touched on it a little bit yesterday at the Smithsonian, but I know that the mission works basically in 200 watts due to the pellets, but how long could the mission go on for? Like Voyager's been going on for well over 25 plus years.
So what makes a mission last? Well, it has to have power. And New Horizons brings its own power with it. And how it does that is this element right here on the back of the spacecraft is a radioisotope thermal generator. And it uses the decay of plutonium-238 into a variety of products, one of which is helium. It's called an alpha particle. It's stripped of all of its electrons. And it gives you a punch, and that velocity can heat things up. And so we take the heat from the decay of plutonium and we turn that into electricity by charging up batteries and then using the batteries. So long as it takes its own power, it's gonna do great. So just like the Voyagers, who also have radioisotope power systems on them, they decay over time. And right now the Voyagers are working on a matter of 10 watts or so. It's going to take several decades before New Horizons will get down to the few watts area. So long as the spacecraft's healthy, so long as its instruments can work with the power that's available, it has the potential to continue to operate. You bet.
All right, our next question comes from Lowell.
This is Pauline at the NASA Social at Lowell Observatory. My question is, will our arrival at Pluto confirm its dwarf planet status, or do you think there's a chance that we, on approach, will have new ideas altogether?
Well, you know, from a NASA perspective, as I mentioned early on, we don't care what we call it. Whether it's a planet, dwarf planet, but I got to tell you, this is a fascinating body. I've never seen anything like it in the solar system. You know, Pluto and Charon are pretty massive, and they do this dance around the center of gravity. You know, the center of gravity between the Earth and our moon is well inside our Earth, and it then looks like the moon constantly goes around the Earth. But that's not what this system is all about at all. It looks more like binary stars, where you have two comparable objects fighting it out as they move around each other. And the moons, you know, the moons are in sometimes chaotically buffered around, and those are also quite fascinating. So this system is nothing like anything we've ever seen. And when that happens, you always want to rethink what you know, and then what you've learned, and then you can move forward with new and different ideas. So let's see what happens next.
All right, one more question in the room here.
Hey, so with what you just said about the center of gravity between the Pluto and its moon, that would infer that there's some sort of stable gravitational orbits around it, kind of like a Lagrange point kind of thing. Would New Horizons be able to look into what's happening there as well?
Absolutely. You know, New Horizons, as it makes its way towards Pluto, is constantly scanning that whole area. We're actually very lucky that the rotational axis of Pluto is lying down more like the plane of the planets, okay? And then that means its moons are displayed right in front of us. So we're able to then see their positions better, understand their masses, understand their relationship between each other, get an idea of how the gravitational resonances are allowing these moons to exist in these locations and not in others. So all that science is going to be done as we take this fly through and get the data.
All right, one more question from Lowell.
Great.
And Lowell doesn't have any more questions. Thank you.
All right then. Well, let's give a round of applause for Jim.
Thank you very much.
Thank you for joining us today.
My pleasure.
All right, up next, we have the principal investigator for the New Horizons mission, Dr. Alan Stern from the Southwest Research Institute. Alan?
Thank you, Jason. Hey, everybody, and good afternoon. Is the mic live? Can you hear it? Great. Okay. Well, I'm excited to tell you about New Horizons, and I appreciate Jim sort of putting it all in context within the NASA Planetary Exploration Program. If we can have the first time step. Go ahead and put the first slide up, David. Yeah, I wanted to show you. This is a sort of cartoony view of our trajectory across the solar system. It starts way down there by the sun, and each of those little white ovals are the orbits of the giant planets, the middle solar system. You can't even see the orbits of the Earth and Mars, Mercury and Venus on this scale. This is really an epic journey, all the way across our solar system to the very frontier of human knowledge and to the very frontier of exploration. We're following in the footsteps of giants named Mariner, first to Mars and first to Venus, first to Mercury. Giants like Pioneer, first to Jupiter and Saturn. And of course, the storied mission, Voyager, first to Uranus and first to Neptune. And Dawn, first to Ceres. These are the planets of our solar system. These are the missions and the mission teams that have, for all of history, opened them up from what Carl Sagan called points of light into true planets where we can actually write the textbooks and understand what they're about, our larger surroundings beyond the Earth, our home solar system. New Horizons has flown since 2006 at record speed, crossing the orbits of Mars, Jupiter, Saturn, Uranus, and Neptune, in each case setting a record to that planet's orbit, and is now on a short course to intercept Pluto in July, on July the 14th, Bastille Day, 2015. You see the third zone of the solar system depicted here. The Kuiper Belt is the largest structure in our planetary system, and it wasn't even discovered until the 1990s. New Horizons is the first ambassador, the first exploration of that region. Its primary target is the Pluto system. Pluto is the largest, the brightest, the first discovered, and the most complex to our knowledge of any object in the Kuiper Belt. It has 5 satellites. It has an atmosphere. It has a moon the size of Texas orbiting so close that they constitute a binary. 4 more smaller moons, and maybe more to be discovered, maybe even rings. It's made of rock on the inside, but it wears an outer shell of ice, and exotic ices, methane, nitrogen condensate, and carbon monoxide. And those generate an atmosphere above the surface that has winds, seasons, precipitation in the form of snows onto the surface. We even see that this atmosphere has doubled in pressure since we've been observing it. And we see that the snows have changed the surface appearance of Pluto. We know it's a complex world. If I can have the next time step, but it's not alone. And I'm going to be telling you about the Kuiper Belt in just a minute. First, I want to tell you about some of the firsts that New Horizons is going to be making. We are, of course, the first mission to the Kuiper Belt, the first mission to explore the Pluto system. But as you see, we're also the first in NASA's New Frontiers planetary exploration program. This is actually the first mission to an outer planet led by an individual principal investigator and team. And there are more firsts there as well. You can read them. But I actually want to tell you about a last that I'm very proud of. and that is the fact that we are completing the reconnaissance of the solar system. New Horizons is flying their anchor leg in a relay that began in the 1960s, in which NASA has been first to every planet and opened our eyes to the true diversity of planetary types, from the middle-sized terrestrial planets to the gargantuan planets of the gas giant region to the small planets of the Kuiper Belt. Next time step. In fact, those small planets are represented right here. These are actual worlds in the Kuiper Belt, the largest members of the Kuiper Belt, including Pluto, of course, to our knowledge, the largest of them all with the most satellites. But you can see, and these are represented to their relative size with their satellites when they're known, to their true colors and reflectivities. And the thing that I want you to notice is the diversity of these planets in the Kuiper Belt. It's something we don't understand. We don't know why they should be such a great variety. You might think, all being formed so far away where it's so cold, that they would be similar. It's a mystery. But with New Horizons, we're going to be able to explore the first of these in depth, and we're going to do it in less than 6 weeks. If I can have the next time step. This is the spacecraft that's going to make that exploration. New Horizons is only the size of about a baby grand piano. At launch, when we had a full fuel supply, it weighed about 1,000 pounds. Inside that spacecraft, which is drawn on the left and shown in a picture taken down at the Cape before launch on the right, inside that spacecraft are all the systems that are needed for the journey. Propulsion, guidance, thermal control, command and data handling, communications. And on the outside of the spacecraft are the 7 scientific instruments, the cameras and the spectrometers, radio science, the student dust counter that are going to be used to explore the system. Now, the 7 instruments aboard New Horizons are something that are really notable because they were very highly miniaturized to fit on a small compact spacecraft so that we could get a very fast launch. The 7 instruments on this payload are the most sophisticated and capable battery of instruments ever sent on a first reconnaissance mission, and yet they weigh combined less than just the camera on the Cassini-Saturn orbiter. And all 7, if you turn them all on at once, draw 28 watts. That's a night light. It's amazing. The power of these instruments is orders of magnitude beyond what was available in our technology in the 1970s to build for Voyager. So we're going to have data sets that are just going to be mouth-watering. We're going to have surface maps. We're going to have color maps, topographic maps, composition maps, and not just for Pluto, but also for the satellites. We're going to search for new satellites and rings. We're going to study the temperature and pressure structure of the atmosphere. We're going to learn the composition of the atmosphere, search for an ionosphere, and do many more things thanks to the capability of this payload. If I can have the next time step. Well, you already know a little bit about Pluto from what I've told you and what Jim had to say. It's a binary, and this is our first trip to a binary planet. And so we're really looking forward to exploring that as another kind of first. 4 small satellites and maybe more. We'll see as we get closer. As I said, Pluto's got an atmosphere, complex seasons, and many other attributes, all the attributes of the closer planets. And its large moon Charon could almost qualify as a planet itself. It's made of rock and ice. We don't think it has an atmosphere, but we're going to search to see if it has one, or if it draws material off of Pluto's atmosphere into orbit around itself. We think that there's pretty good circumstantial evidence that Charon could be active, geologically active today, from some of the chemical clues we've seen in spectroscopy from Earth and from Earth orbit. So we're going to be on the lookout for those signs of activity and for more telltales in terms of its cratering record, for example, its geology, whether it has tectonism, whether there could be geysers, slurries from cryovolcanoes on the surface, or other things. Some geophysical models even predict that Charon may have an ocean on its inside. How's that for wild? Next view graph. This is one of my favorite pictures. It's the best picture of Pluto ever made from Earth. It was made by the biggest, baddest gun that we have, the Hubble Space Telescope. But from 3,000 miles away, it's not much because Pluto's so far away. Let me contrast that. If I can get the next time step here, this is the kind of imagery that we will have of Pluto in just a few weeks. These are images of the Earth at resolutions comparable to what New Horizons will deliver on Pluto. The globe that you see there, the Earth, not very pixelated, a beautiful view of the Earth. That's about the view that we will have one day before we arrive at closest approach. And our very closest images will be as good as this image of New York City. And I realize on the television camera you may not be able to see everything we can see in the room, but that's Manhattan Island in the middle with the Hudson on the left and the East River on the right. You can see, staring at our screen, you can see Central Park. If you look very carefully, you can see the ponds in Central Park. You can see wharfs on the Hudson. That's the kind of resolution that New Horizons is going to deliver when we get there in 6 weeks. And that's just what we'll do in terms of the simple imaging. When we add to that the thermal maps that I talked about, the stereographic maps that let us reconstruct the topography, the composition maps, all the different studies of the atmosphere, and all the other things that we're going to do, we're going to write the textbook overnight, and we're going to bring you along for the ride, not just on NASA television, but also with social media, with websites, with instantaneous image releases, next day image releases, and we're going to answer your questions along the way. We're basically doing one of the historic missions from the 60s or 70s with 21st century spacecraft technology and 21st century media sensibilities. We can't wait to bring you along. And thank you very much, and I'll take your questions.
All right. Just a reminder for those who are following along online at home, we're taking your questions using the Ask NASA hashtag. So our first question comes from a Twitter user, Jonathan, who asks, what does the behavior of the moons imply for the presence of potentially hazardous debris in the path of New Horizons?
That's a great question. For those of you who don't know, we're being very careful. We know that Pluto's smallest satellites have so little gravity that when they're cratered, the material that comes out of the hole in the ground, the ejecta, gets into orbit around Pluto. And because our spacecraft is moving so fast, even an impact by a rice pellet-sized pebble or piece of debris from those moons could cause great damage. So we're conducting a hazard watch on the way in. We haven't found anything that's concerning yet, and the best numerical models indicate we probably never will. But we're not taking any chances. So we prepared backup plans. And I think what the questioner is asking is about the new discoveries that were just announced from the Hubble Space Telescope, that Pluto's small moons are rotating chaotically. That probably doesn't affect the amount of debris that could be in the system or the hazards to New Horizons, but it's a really good question, and it's very topical.
Wonderful. Do we have a question in the room? All right. Wait for the microphone.
Hi, yes. I was wondering, what instruments on the spacecraft do you use to test the chemical composition on Pluto, and how do they work?
That's great. We have spectrometers on board that tell us about the chemical composition. We have 2 spectrometers. One is an ultraviolet spectrometer, which breaks up the light in the ultraviolet band into its individual wavelengths so that we can see atoms and molecules glowing from their interaction with sunlight. And that lets us fingerprint the composition of Pluto's atmosphere. And it will also let us determine the density of the atmosphere as a function of altitude. We also have an infrared spectrometer on board that works in similar ways optically, but in the infrared part of the spectrum. It breaks up the light into its individual wavelengths, but the infrared is useful for studying the surfaces of worlds and studying their composition. So the ultraviolet spectrometer is called Alice, and its honeymooner is Ralph. Ralph is the infrared spectrometer, which will map the surface compositions of Pluto and all of its satellites. Thank you.
Wonderful. Our next question is going to come from Lowell.
Hi, Enzo Vito, Lowell NASA Social, Embry Riddle Prescott. Dr. Grundy informed me that there is no magnetometer on board, so to what extent can Pepsi and SWAP measure Pluto's magnetic field, and will it be enough for possibly a follow-on mission? Thank you.
Okay, that's a great question. So a little bit of background for everybody else. Pepsi and SWAP are the 2 instruments to study charged particles, plasma, in the Pluto environment. And actually, they've been used to study the same thing, those charged particles, all the way across the solar system as we've transected the entire heliosphere from 1AU all the way out to the Kuiper Belt. And Pepsi and SWAP are primarily there to study the gases coming off of Pluto's atmosphere, escaping from the atmosphere, and to determine its escape rate. But in addition, some of the signatures that they may detect could reveal whether Pluto has a strong magnetic field or not. Now, according to standard theory, small worlds, small planets, and asteroids don't typically have strong magnetic fields. And we made a choice. We had to make many choices in order to get a mission to Pluto to not carry everything that you could possibly think of. And a magnetometer was deemed to be one of those things where we were taking a big bet. Pluto probably doesn't have a magnetic field, so we left that off the payload. But we know that if Pluto has a strong magnetic signature, that will not only surprise the geophysicists, it will make itself known in the data from Pepsi and SWAP. So our team that's called the Particles in Plasma, part of the science team, is very anxious to see the data from the closest approach to see whether they're surprised by that.
All right, next question comes from here in the room.
Hi, Dr. Stern. Thank you for taking these questions. So I learned today that the data from Earth to New Horizons will take about 4.5 hours, and then it'll be another 4.5 hours before it comes back. And I want to know if you had any plans for that 9-hour window, maybe some golf, or maybe a nice show or a book. It's been a while, so.
Yeah, let me tell you a little bit about closest approach. We designed New Horizons to be extremely effective when it's there. We have very fast bus speeds on the spacecraft, so we can take data from up to 5 instruments at once. We have very large solid-state memories by spacecraft standards, so we can store a lot of data. In fact, we take about 100 times as much data on closest approach as we can send back in a single day. So New Horizons is going to be the gift that keeps on giving. Long after we pass the Pluto system, new images and new spectra will be coming to the ground for the science team and for all of you, for everyone. Now, as we make our journey through closest approach, we have a choice and we made a long time ago, which is we can either take as much data as possible or we can talk to the Earth. And we chose to take as much data as possible. So on closest approach day, the spacecraft actually won't be communicating with Earth until late in the evening. Its last image before closest approach will come down late on the 13th of July. And all throughout the 14th, there'll be no images. The big download begins on the 15th, Wednesday the 15th. And that data does take 4.5 hours from the spacecraft to reach Earth. But after one image comes down, the next one comes down, and then some spectroscopy, and then some data from Pepsi and SWAP and other data types. And that'll continue day after day for a couple of weeks. Then we're going to take a break for a little while, give the mission operations team a well-deserved rest. And then we'll come back and start a more than year-long downlink to empty those memories back to the Earth and fill up the data banks here.
All right, wonderful. Our next question comes from Lowell.
Hi, Alan Stern. Thank you for taking the question. This is Michael Kaiser from the NASA Social at Lowell. So my question is a follow-up to the spectrometer question earlier. Will we be able to determine the full chemical makeup of Pluto's atmosphere, and will we be able to determine the proportion of those molecules? I was just wondering about the resolution of the spectrometers.
Yeah, if you're into the resolution of the spectrometer, the spectral resolution over the entire bandpass, which runs from 1.25 to 2.5 microns, is about 250. And we have a high resolution segment with about twice that resolution, a spectral resolution of about 500. We're going to be able to determine the composition of the atmosphere as a function of altitude. That includes the density of each species that we can detect. There are quite a wide range of hydrocarbons and nitrogen-bearing molecules called nitriles that we can detect, and we'll be on the lookout for those. We could also detect water vapor and many other important molecular species. We can detect individual atomic species high in the atmosphere, like hydrogen that we think is prevalent in the top of Pluto's atmosphere. And we'll be able to look for evidence of hazes and clouds, both with our cameras and our spectrometers. So it's a pretty comprehensive investigation of the atmosphere.
All right, again, we're taking questions online using the hashtag AskNASA. This next question comes from Twitter user Professor Abel Mendez, who asks, what's the best estimate now on the total atmospheric pressure of Pluto at the surface level?
Well, the best estimate is determined from Earth-based studies that observe the very occasional disappearance of a star behind Pluto in its reappearance. And by graphing the rate at which the light declines due to atmospheric refraction and then comes back, we can actually determine things like the scale height and the pressure in the atmosphere. The thing that we don't know is whether we're seeing to the bottom of the atmosphere. So what we have is a lower limit on the pressure, and that's about 10 microbars. But the atmosphere may be deeper than we can probe from Earth-based techniques like occultations. New Horizons will determine that. And it's entirely possible that the pressure could be as much as 5 or 10 times higher, 50 or 100 microbars. That's kind of the range of our uncertainty, and there will be no uncertainty after July. We will tell you the answer.
All right, another question in the room.
Hi, Doctor. I'm Emily Bondrick, a history teacher at Morris Tech in New Jersey. And well, first of all, I want to say I appreciate the Bastille Day connection, because it's, in a symbolic way, this is just as revolutionary. My classes learned this year that Director Bolden said that the missions in outer space help us learn more about Earth. So is this mission more that we learn about just what human progress and potential can do? Or can we actually learn more about Earth from this mission, or is it more the later missions that we'll get after this first one occurs, if that makes sense?
I'm really glad you asked that question. It's an excellent question, and we can learn about the origin of the Earth in 3 different ways. The first is by studying the Pluto system itself. By studying small planets, we can learn about how the building blocks that were the lumpy potatoes and planetesimals of the solar system built small planets out of which bigger planets came to exist. And we've never studied any planet like Pluto before. So that's the first way. The second is that the origin of Pluto's satellite system is strongly believed to be the same origin mechanism, a giant collision that spalled material off of Pluto and into orbit, where it coalesced into the satellites that formed the Earth-Moon system. In fact, the Pluto system is the only known example in our solar system of a formation mechanism for its satellites like Earth-Moon. So it's very important to planetary scientists to have that second example. And we've known that that was part of the motivation for going to the Pluto system, was to study the origin of its big moon Charon, in analogy to the Earth. But there's also a third way. Pluto's atmosphere is rapidly escaping, in part because Pluto is a small planet, and in part because there's a heating mechanism in the upper atmosphere that adds energy to the molecules. And the escape rate of Pluto's atmosphere, the escape mechanism, is called hydrodynamic escape, which is a fancy term, but all it really means is that the escape rate is much higher than normal. It's due to that high temperature. And the same thing took place on the Earth. Right after the Earth formed, when it was still molten, its atmosphere was hydrodynamically escaping. Originally, Earth's atmosphere was made of hydrogen and helium, but that's all gone now. That's the process through which the hydrogen and helium left, was hydrodynamic escape. It's been discovered by theorists on blackboards, and it's been modeled in computers, but it's never been observed on a planetary scale. Pluto is the first place where we can go to study a process that fundamentally reshaped the Earth's atmosphere from a poisonous hydrogen and helium envelope to the atmosphere that we enjoy today. So that's another connection.
Thank you, that's awesome.
Wonderful. Our next question is going to come from Lowell Observatory.
Hi, my name is Casey, and I'm wondering when we might see an orbital mission, or if you could even speculate as to a rover mission or some sort of landing, and what we could learn more from these as opposed to just a flyby mission. Thank you.
Well, it's hard to predict something like that, but I can tell you that if Pluto's as interesting as we expect it to be, like Jim Green said, I think that the scientific community will want to go back and make more detailed studies. And an orbiter or a lander is a beautiful mission to fly next. Of course, to make the case for that and then build the mission and to fly it out is probably a couple of decades. Maybe that's a mission for the 2030s, after we fly to Europa and learn about its interior oceans, fly our next Mars rovers. That might be the next kind of major mission, but it really depends upon the results and how exciting they are from New Horizons. So that's the kind of thing I'd like to talk about a little bit later down the road, because we're really focused on the first reconnaissance of the Pluto system for now.
Interesting question came in on Ask NASA here, asking from Twitter user Ciro Via, who asks, what will be the next object that New Horizons will be visiting after Pluto?
Well, after Pluto, as called for by the Decadal Survey in planetary science, we have an opportunity to go farther into the Kuiper Belt and study those building blocks, those planetesimals that the dwarf planets like Pluto, Eris, Makemake, Sedna, and so forth were built from. In fact, we've identified 2 potential targets within our fuel supply, within our reach, And both flybys would occur in 2019. We can go to one or the other, but they're in different directions, so we have to choose between them. And we're going to be doing that in August. But for that mission to culminate, for it to actually take place, we have to write a proposal, as all extended missions do, to NASA, and that'll be peer-reviewed. And if it's well-reviewed, then NASA headquarters will make a decision to fund that mission out to 2019 or 2020 to capture that data, get it all back to the Earth. And we're looking forward to writing that proposal very much because we think it's exciting, and we think that the opportunity to go another 1 billion miles and explore the pristine objects out of which the small planets like Pluto were made is an unprecedented opportunity that no other mission that's on the drawing boards or in flight can accomplish. That's something New Horizons can uniquely contribute. And so we're very much looking forward to the opportunity to propose that.
All right, another question here in the room.
Hi, Dr. Stern. So those two objects, what's going to be your criteria for choosing which one you do eventually target?
Another good question, and there are a whole variety of criteria that we're looking at. They have to do with how much fuel we have to do each mission and how exciting the science is, because one takes more fuel to reach, takes almost all of our fuel supply just to get pointed in its direction to intercept it. The other one takes about half our fuel supply, leaving a lot more for the actual scientific observations when we're there. We're also looking at our ability to communicate, how much power we'll have on the spacecraft years later. You heard from Jim about the half-life for radioactive decay that lowers the power every year when you have an RTG power supply. We're looking at the lighting levels, the sizes, estimated sizes of the objects, and also their provenance or their origin. Turns out both objects come from an ancient population called the cold classical objects of the Kuiper Belt that were actually formed in this very region of the solar system, not transported out to the Kuiper Belt, but formed there. So they actually tell us about the conditions there in the beginning. So all those factors go into the mix, and the team will make a recommendation to NASA later this summer. And then in the fall, we need to fire the engines, because the longer we wait, the more and more fuel it takes. And even if you wait till late 2016, just a year later, both missions would take more fuel than we have on board. Thank you.
All right, last question for Dr. Stern comes from Lowell Observatory.
Lowell has some more questions. Thank you.
All right, then. Thank you very much for joining us today and answering
Absolutely.
questions.
Thank you.
Definitely. So you've heard a little bit about the science of what New Horizons is going to accomplish, but none of that would happen without the hardware. So we're going to get up here and talk a little bit now for a few minutes about the actual spacecraft itself and what's on board and everything. So up next to join us here is Chris Hersman, who is the Mission Systems Engineer here at the Applied Physics Laboratory. Welcome, Chris.
Thank you, Jason.
Definitely.
So it's my pleasure to give you a tour of the spacecraft. This is my favorite part of the mission, but unfortunately, it's our job to carry those instruments to Pluto and take all those observations. So I was involved in the development. I was the spacecraft system engineer when we were building it, and then was promoted to the mission system engineer after launch. And I'm going to go over, give you a little tour around the spacecraft. You've heard a lot about the instruments already. Just to give you a perspective on the size, I always use my arms. I stretch my arms out and say that the high gain antenna, this white dish, is just a little bit longer than you can reach. It's about approximately 80 inches. And the whole spacecraft, you heard, it was like a grand piano. And you'll notice that on this end of the spacecraft, this is all hanging out by itself over here. And you might say, well, why is that? And there are a couple reasons for that. First, it provides balance for the spinning mode of the spacecraft. And I brought a little prop here to describe that. It was very expensive to make, but so they wouldn't let me throw the models around. So but by balancing the RTG, which is the power source, out on the end by itself, and all the instruments on the other side, you get something that'll spin, and then you don't have to use thrusters to keep the spacecraft pointed at the Earth. So if you all were the Earth and it was spinning this way, that way you'd keep the high gain antenna pointed at Earth without using any fuel. So that's a way that we can get out to Pluto without having a lot of extra fuel on board to keep the spacecraft pointed. Because when we're in a 3-axis mode, which is where what we're doing at Pluto, the thrusters, which you'll see here, there's thrusters scattered around the spacecraft, and they're precisely positioned so that you can maneuver any way. But in order to point to the Earth when we're in a 3-axis mode, which is our steering mode, you have to thrust back and forth to keep the high gain antenna focused on the Earth. And that uses fuel, it uses thruster cycles, and those are consumable on the spacecraft. So I'm going to move down to the first instrument that we're going to talk about, which is ALICE. And this instrument is the ultraviolet one. Alan told you a lot about it. So if you have questions about the details of that, you'll have to go back to Alan. But I did want to talk about how it's used. There's an aperture pointing in this direction, which gives you the occultation measurement simultaneous with the radio science experiment. So the high gain antenna is pointed at the Earth at the same time as the little aperture on the side of ALICE is pointed at the Sun, and they both measure as they traverse through into the shadow of Pluto, and they traverse through the atmosphere and make measurements along the way. And then, as you heard earlier about the air glow, this is where the measurements are taken where you're looking at Pluto, and it's much more sensitive. So this one, the solar occultation channel, looks at the Sun. This one, the air glow aperture, looks at Pluto. And then we'll move on to the Ralph instrument, which is the infrared and visible camera on the spacecraft. And you'll notice this big white area is a radiator, and that's to keep the infrared part of the instrument very cold. And it's a double radiator because the spacecraft is very warm inside. Well, it's room temperature, which in space is very warm. And then this instrument is very cold. And so what they do is they have 2 radiators to keep this radiator very cold. Then this one actually isolates even further, and then there's a feed that goes in there and connects to the electronics that's the detector of the instrument. And that keeps the detector very cold so that when it takes infrared imaging, it can get less noise in the measurement. So now we'll move around to the other side of the spacecraft, and you'll see the radioisotope thermoelectric generator. And you'll notice it's black. It's also very hot inside, and the heat from the inside and the cold outside in space allows us to generate electricity from that temperature differential. And it only generates about 200 watts when we're at Pluto, but it generates a lot more heat. So we actually save some of the electric power by putting a little hole in the end of here inside the spacecraft, and we recapture some of that heat and put it back into the spacecraft to keep it warm. And there was a lot of calculations that went into the design of how big that hole should be. And we actually tested it in thermal vacuum chambers here on Earth before we launched, and it's been working perfectly. Then the other thing we do is once we get the heat that we really want to keep in the spacecraft, we want to reject all the other heat, which is what this little shield is for. It keeps all the heat away from the other instruments because they don't want to be kind of altered by that heat. And then you'll notice here there's a pyramid shape, which we actually were able to adjust the design to help balance the spacecraft. And in the development, we actually changed that a little bit, not physically, but in the design phase, to help balance out once we figured where all this things would be on the spacecraft. So now we'll go up to the high gain antenna, and we'll see that there were a lot. This is the assembly of the high gain antenna, and there were a lot of antennas on here. The low gain antenna was used at launch because it can see one hemisphere of the spacecraft, of the Earth, or wherever it's pointed, and then there's another one just like it on the bottom side. So that way, if the spacecraft comes off and we're pointed in some odd direction, we can talk to the spacecraft. Right now, though, it's so far away that these are useless now, and so we don't use these anymore. We have this medium gain antenna, which we use for our beacon mode, and when we're in a spinning mode and we're not pointed directly at the Earth, we can use this to tell us that the spacecraft is fine. And what we do is we point it in a specific direction where in the future the Earth will be right in the center of the antenna, and that way we can talk to it once a week and say, actually we can listen to it once a week, and the spacecraft will say, everything's fine, and I'm doing what I'm supposed to be doing. And then the high gain antenna is the one that's really important for the REX observation. That's the radio science. And we use that. You can see, in case you wondered, the radio signals come on and bounce off this large dish, and then they also reflect off of the backside of this antenna and then go into the feed of the antenna. And that allowed us, the combination of this and that allowed us to shape the beam so it's not just a round beam. It's actually shaped in a way that gives you kind of a flat top of the gain of the antenna. So that provides us with our high gain beam width, and we get a little wider beam width, which helps save on thruster usage. And now we'll go to the next set of instruments, which are on the other side of the spacecraft. This is the solar wind at Pluto SWAP experiment, and you can see the launch doors are deployed, and it has a very large fan-like field of view. All the way around here is where it can receive signals, and the advantage of that is that while the cameras are all pointing around and looking, this can still make its measurements because it has such a wide field of view in this plane. And the same with, if we go up to the Pepsi instrument, it also has a fan beam antenna, which you can see up here. And I think it'll go soon. Is the video moving? There we go. So you can see here the fan beam of the energetic particle instrument. This is Pepsi. And then there's also this, this here to shield the solar influence. Actually, it was to shield the high interactions with the high gain antenna because of where it's placed. So now we're going to go around to the long-range imager, which is on the backside, which is the biggest aperture. This is about 1 meter across, or about a yard. And that is what we take the approach images with, and for navigation. So when we're going up, we're going to take pictures of Pluto and the stars in the background and figure out, better than we can do on the ground, where Pluto is with respect to the spacecraft. And then we actually adjust the time of the commands that will take all the observations so that they're synchronized with where the spacecraft is. And then we'll also send up an ephemeris so we can, so that everything will be in lockstep with the way we planned it. And then over here you can also see the star trackers. These are used for attitude, to determine where the attitude is. And there's 2 of them for redundancy. We only need 1, but we put 2 on board. And we have what we call our autonomy system, which will switch from one to the other if one isn't working. And that is an important part of a spacecraft that's going to go and be 9 hours away. If we wanted to tell it to do something, we wouldn't know whether it did it until 9 hours till we get the message back. So it's got to take care of itself and tell us what it's doing. And so on board is an autonomy system that has rules that check on telemetry on the spacecraft and switch things to redundant components if necessary. And when it does that, it reports back. And if for some reason it couldn't use these, next we'll go up to the sun sensor. We have a mode of the spacecraft that says, I don't know anything, I'm lost in space, I'm going to point to the sun, because the sun, when you're so far away at Pluto, is very close to the Earth. So if we point to the sun, then the Earth will be able to talk to the spacecraft. So it's not actually because we need power from the sun, but because we want to communicate with Earth. So that's pretty much the tour. And I think, yep, that's it. So if you have any questions.
Indeed, questions about the spacecraft. First question in the room. Let's go up here.
Could you talk a bit more about the thrusters and about the changing of modes from spin to 3-axis and so on and so forth?
Sure. So I could use the model, I guess. Let me do this, because I always like to, I think this comes off of here. So, and actually we can see the bottom too, because that's where the propellant tank is, right under here. So, the thrusters are in groups around the spacecraft. So there's some down here on the bottom, and there's some on the side. And what they do is they fire in pairs. So if we wanted to spin this way, we would fire one here and then one over here. And they're pointed in general, let's see, if we, this way and this way on the top and the bottom, and then this way and this way on the sides. So the ones that are on the sides tip it this way, and the ones that are on the top and the bottom go this way and this way. And so you get 3-axis control. And so when we want to spin up, we fire the thrusters and spin at 5 RPM because that's a fairly stable. It's a trade-off between, there's always trade-offs, but it takes fuel to spin up, and the faster you spin, the more stable you are. And so we probably could have gone slower, but we budgeted to have 5 RPM, and once everything is working, you don't want to change anything. So there are two other thrusters I forgot to mention, which are the delta V thrusters. So there's 2 thrusters pointing straight down out of the bottom, and those are the ones we use to do this maneuver after Pluto, where we go to the Kuiper Belt. They're much bigger. They're like 5 times as big. And then when we do that, we also use the other thrusters to control the pointing as we're thrusting. One other neat thing is that we only use 2 thrusters at a time because the thrusters take a lot of energy, and so we want to always stay under that 200 watts of power. So we only operate 2 thrusters at a time, except for when we're doing a delta V, and then we can use 4.
What's the fuel source?
Hydrazine. It's a monopropellant hydrazine.
All right, next question comes from Lowell Observatory. Lowell?
Hi, Enzo Vito, Lowell NASA Social, Embry-Riddle Prescott. How has the use of RTGs on New Horizons changed the attitudes, political or otherwise, of utilizing radioactive material for power systems for deep space missions? Thank you.
That would be a more programmatic question as far as, I could tell you that there wasn't much resistance for New Horizons because it was a direct launch into space, so there weren't any flybys. It also had 1 radioisotope thermoelectric generator and no other radioisotope heater units. So the analysis for the safety was very straightforward and simple, and we made a conscious decision to do that because we had a short schedule. So we were launching a power source that had already flown, already in this configuration similar to like Ulysses, and so the analysis was pretty straightforward and safe, and so I think we would have to poll the audience or the the public to see how it has changed their perception. But I never had any concerns about the launching of the power source.
Wonderful. Just a reminder for everyone following along online, we're taking questions using the hashtag AskNASA. So this question comes from Twitter user Turin, who asks, how long will New Horizons last in space?
So that's a good question, and it depends on what things could go wrong first. So, or if everything goes right, there are things that you can do that take on more risk. So as you mentioned about the propulsion system and the thrusters, as we start losing power from the RTG, it starts to decay and go down. You think about what can we shut off and what don't we need? And there are actually ways that you can operate the spacecraft with less thrusters, and you could allow them to get colder, and the temperature, you could allow that to get a little colder. But as you do, you're taking on more risk. We've actually calculated that if all things go well, we can confidently maintain until the mid-30s, 2030, 2030s. And that's, but if you asked me and said I was betting, I think we could go longer than that. But we had to kind of estimate what's a reliable mission life and calculate the decay in the RTG, and we came up with the mid-2030s.
All right. Next question from in the room.
With that, to follow up on what you just said about the 2030s,
Mm-hmm.
and then earlier Alan talked about the decision about going which direction.
Mm-hmm.
Let's say that it lasts beyond 2030. Is there any future plans beyond the next venture for New Horizons?
Yeah, there is actually some future plans. But of course, they can't be decided on until there's funding and all of that. So from an engineering and scientific, the advantage of going longer is that you can take the measurements from the particles and plasma instruments and measure the interaction between the heliosphere and the the galactic medium. So that right now Voyager has transferred into out beyond the heliosphere, and the interactions that they discovered in that boundary was very surprising. And so we would actually be able to make another measurement in another part of the heliosphere, and see that transition into, I guess, outer space you'd call it, but it's beyond the solar influence.
Next question comes from Lowell Observatory.
Hi, my name's Natalie Felder, and my question is, what is the exterior body constructed of to withstand the vacuum and pressure of deep space, and how vulnerable is it to the elements of the unknown, so to speak?
Oh, that's a good question. So the vacuum is not a problem because there are vents that let the air out. So when you launch and you go into the vacuum, all the air that was inside vents out. So now it's a vacuum. So that's not a problem. But for the protecting against micrometeoroids, what we did is we took the thermal blankets and we put standoffs all around the spacecraft. There's like little toothpicks, sort of, or little standoffs to raise the blankets a little bit bigger. So when you saw the spacecraft with the blankets, they're not pressed right against the spacecraft. They're actually stood off as like a bumper for the very small particles that might be in space, to allow them to hit something and then disperse before they so that they won't penetrate the surface of the spacecraft. And then we also put a very dense layer of Kevlar in the blankets. So we have the thermal blankets, but we also have a layer inside of there that's very strong. It won't stop the particle from getting through that blanket, but what it will do is break it up so that when it does hit the deck of the spacecraft, it won't penetrate. It'll just make an indentation. So that's how we designed the spacecraft for that.
All right, next question in the room here.
Alex Orfanos from Today in Space. Thank you, Lowell, for that last question. Perfect segue. How is that attached? Because it looks so thin, and is it a tape or
the blanket?
paste?
Yeah. They have, I believe it's Velcroed as well. So one of the things that we did in our testing is that we had to be very accurate about how much heat was leaking out of the spacecraft. And so in order to prove that we could do that, we actually had to put the blankets on, test it in a thermal vacuum, take the blankets off, and then put them back on again and make sure it was the same, so that when we put them back on the last time, we could have confidence that it was going to be the same. So I believe it's Velcro and tape, and then the standoffs have like a little, it's like a washer or something that holds it up, and then it's fastened on the top. So, but we have amazing thermal engineers that will sew these blankets, and it's really quite an operation. They have a whole model of the spacecraft, and they build it on the model, and then they have to piece it off. It's like a custom dress or something for the.
All right, last question for Chris comes from Lowell.
Hi, Allie McGraw here. My question is about spacecraft jitter. Are there any of the instruments that you expect to see any jitter, or were they designed to be on the spacecraft where they would get the least amount?
Right, so we tried to avoid moving parts wherever possible to increase the reliability of the spacecraft. So there's really nothing on board that has to move. There is, the student dust counter is one that can measure very fine disturbances, because it's intended to measure a very small impact on a detector, but it has the ability to set its threshold. So, and the one thing I was going to say that does have moving parts is there's a valve inside the thrusters. And so the student dust counter can actually detect when those thrusters are firing. And so when we're at Pluto, it actually has to raise its threshold as compared to when it's in hibernation. So when we're in hibernation, we don't fire any thrusters, and they lower their threshold to be more sensitive. And then when we get to Pluto, we're going to be thrusting and maneuvering and taking pictures, and that actually causes slight disturbances on the spacecraft. But there really is no jitter as far as the images are concerned, only the motion of the spacecraft and the attitude control.
All right, thank you very much, Chris,
thanks,
for
Jason.
letting us know about the spacecraft.
All right, I'll see you there.
Definitely.
Thank you.
All right. Up next from NASA's Ames Research Center, we have Kim Inico. She's here to tell us a little bit about what it's like to be on the team and the preparations that they're making for the July 14th flyby of Pluto. So, Kim?
All right. So being a NASA social, I want to convey to you a day in the life of what's going on right now. We are 37 days from closest approach. We are in day of year 157, and a lot of times these numbers and dates are in my head because in the course of a single day, I may be thinking about something that was months ago, weeks ago, this morning, tomorrow, next week, and the next year. So doing this juggling. So I just want to give you a sense of a day in the life of the operations. The mission is long, 9.5 years, launched in 2006, gets to Pluto in July 14, 2015, 9.5 years. But it hasn't been, you launch it and then you put it to sleep and you forget about it for 9 years. What this graph represents here is 7 years of the mission scrunched down into a slide, color-coding time from left to right, the different periods of activities. Typically, after launch, instrument checkout, the Jupiter flyby, which occurred a 1.5 years after launch, went into this cruise mode. During the course of the cruise mode, the instruments would go to sleep for several months of the year and wake up about twice a year, for which we would do calibrations, see if everything is fine, checking whether the temperatures were working well. So this has been the course of action for the last 7 years. The colors here represent, purple is when it's in the spin mode, which Chris had alluded to. We go into spin mode. It gives us a stabilization for the antenna pointed at Earth, saves on fuel. We're not taking any pictures then. Those yellow periods here, short, just a week here, a week there, twice a year. That's when we go to 3-axis mode to do some observations. If we go to the next slide, 2015, our encounter started in January. Yes, July 14th is going to be the day, but our team is really busy right now. In fact, it's very busy right now. And I've indicated a red line. We're at June 6th, about P minus 38, P meaning Pluto minus 38 days. What you see here is just an expanded of 2015, is that we woke up of hibernation in December of last year, went into 3-axis mode, and started a series of optical navigation using the LORRI instrument to look at Pluto, Charon, and Nixon Hydra with 2 different modes and measure precisely where we're pointed, because we used that information and did a correction maneuver a few months ago. And we are planning the next maneuver on June 15th. However, that's not certain because the team today is looking at data that was taken down 3 days ago that got brought down today, and they're looking at it right now, analyzing it, and a decision will be made on Monday whether or not we're going to go ahead with a burn in a couple of days. So it's very busy right now. Just to give you a sense, when we get to July 14th, a couple of days before, the bar turns orange. That's just an indication that we've put the spacecraft into a particular mode called encounter mode, where autonomy aboard the spacecraft will reboot the computer in case we have a CNDH, a command and data handling event failure. We have this one opportunity to do the flyby, and we can't wait for the spacecraft to go safe. So we have a special mode that was tested. We tested it during a rehearsal a 1.5 years ago because we wanted to make sure that the spacecraft, all the systems on board the spacecraft would execute. So doing a full rehearsal of what we would be doing with the spacecraft this summer, this July, 2 years ago, retired a lot of uncertainties of how the actual spacecraft will behave. Go to the next slide. I wanted to point this out. If everyone doesn't know about this amazing site, eyes.nasa.gov/DSN. This is a screen grab of April when we did a test simulating the ground support we needed for a particular type of experiment that we're going to do during the Pluto and Charon occultations called the uplink experiment. And what you can see here is this is the three Madrid, Goldstone, and Canberra, the DSNs, and we actually had 5 antennas in use. Now we've switched to live, and I want to point out, if you go to it right now, eyes.nasa.gov/DSN, you will see we are actually talking to Canberra right now. Our call sign is NHPC. This is a 70 meter, the larger dish. These are 34 meters. Today, we are downloading data that we took the last couple of days. In fact, today's data, it has been earlier in the morning. It was some optical navigation. And right now, we're getting down hazard data. We call it hazard data or moon search data. We have strategically looking at the Pluto system, looking for moons to inform the project whether or not we need to make a course correction. We haven't seen anything to date, but we're still taking these looks. We have specific times in the timeline when we can make a decision whether to go to a slightly different trajectory or a slightly different spacecraft attitude. We are showing you the latest images from the LORRI camera, posting on the JHU APL website. If you go to the main website, and there's this little camera icon, it will show you the LORRI images. And here's one. Okay, this was a screen grab I do, but if you look right now, you'll see it's a data taken from June 6th that are showing there right now to show you the system. And you can look on the thumbnails and follow along now. As my message is that we're not waiting till July 14th. I mean, July 14th is going to be epic. The spacecraft's going to be busy taking pictures of Pluto. We're going to be sitting back and waiting. But right now, we're actually taking some new data that and communicating with the spacecraft and doing lots of decision making right now. We can move on. To give you a glimpse, I was going to give you a sense that in a current day right now in my life, and also in the life of a team, because I do want to quote one of my heroes, Emmett, from the Lego movie, that everything is awesome, but everything is cool when you're part of a team. The whole team aspect is just crucial because we have to have so many eyes with so many different disciplines reviewing the data products. So I had hinted that in a course of a day, I could start my morning having a conversation talking about something we did 3 months ago, sitting in a review of something that's going up to the spacecraft 2 days from now, to planning the downlink of the data that's going to occur over the next year and a half. This is an example of a load that we were just reviewing that is for after the flyby, the first load after the flyby. To give you an example of a planning products that we have to remove. What you see here is the green, this is an STK image, and the green represents the field of view of the LORRI imager. And as to quote one of our sequencers, when she made these images for the science team review, she said she got all sad because Pluto and Charon started getting smaller and smaller and smaller and smaller as we're going further and further away. Also, the illumination is different. We fly in when Pluto and Charon are illuminated, like gibbous. But then as we fly through the system, become thin crescents. So they become darker and more just very different worlds. And we have a specific series of images that we're going to take, looking back at these thin crescents to look for dust, to keep on understanding the system, because we're not going back. So this is something that we're planning for July 21st. Okay? And it had been mentioned before that we are downloading data right now. We're in June, and we're getting data that cover all different types of sciences. So we're taking the data and downlinking as best as we can. When we get to the actual July encounter, we have to fill up those recorders as best as possible. We're not downlinking that much because every second looking at Earth is a second not looking at Pluto. And when you pass through the Pluto system at 36,000 miles per hour, 50,000 kilometers per hour, you pass into the system, you want to take as many pictures and as many spectra as you can. So we just fill up those hard banks. And then we have a couple of snippets of data, then starting in August, going out for a year and a half, we'll be downloading this data. So, and I've been involved in planning for that. So in the course of a day, I've been thinking about the past. I'm looking at data. I'm doing science. I'm helping review what's going up to the spacecraft in a month's time, in a week's time, in a couple of days' time, thinking about the future. We're preparing for the encounter. Today, we're getting data down for the nav and hazards team. They're analyzing the data right today, right now, because they need to make a decision on Monday. So it's a very active period for the whole team. And you can follow us along by always looking at that DSN website. It shows you when we're in connection. We're not talking to a DSN all the time, but we do talk to it several times a week. And also looking at the website to see the latest images from Lori. So it's a very, very exciting time right now. And we haven't even made it to July 14th. We got 37 days to go.
All right. Thank you very much, Kim, for sharing with us a little bit about what the day in the life of the team looks like, how you guys are getting ready for the preparations and everything. And Kim's active on social media, and so she can definitely answer some of your questions on there. If you use the Ask NASA hashtag, she can get you some answers to some of those out there. So wonderful. All right. Yeah, so next up, in the interest of time here, we want to give one big way that you guys can get involved in following along on the flyby. So you saw a glimpse of all the planning that Kim was talking about here and everything and so on, and you can actually see with NASA's eyes on the solar system, with their eyes on Pluto module that they've got, a little bit of how you too can watch and follow along during the entire flyby sequence and everything. So here to tell us a little more about it is Kevin Hussey from NASA's Jet Propulsion Laboratory. Kevin?
Thank you, Jason. Yes, I manage a group at the Jet Propulsion Laboratory whose job it is to visualize data, both engineering and science data that NASA collects. And one of the tools that's already been mentioned is NASA's eyes, eyes.nasa.gov. So my objective here in the next few minutes is to train you how to become virtual explorers of the solar system using eyes.nasa.gov. So I'm just going to walk you through the process. You start by going to the website, eyes.nasa.gov, and when you do, you'll see a big download button. When you hit download, you literally are going to be downloading essentially is a video game. We use video game technology to allow you to visualize what's taking place in the solar system. Now, I've already done that, obviously, so I'm going to minimize this. Once you do download it, you're going to get an icon on your desktop that says NASA's Eyes. By the way, this is a live demonstration. I've been warned about doing live demonstrations, but it doesn't scare me. So I'm going to double-click this to actually show you what it'll be like once you download this software. We have many different products. We have one that talks about the Earth. We have two for the solar system. And we have one for exoplanets, planets that have been discovered around other stars. We also have these links at the bottom, which are subsets of Eyes on the Solar System. Okay? One of which is called Eyes on Pluto, and that's the one I'm going to be spending most of my time on today. Before I do, I just want to make a note here that Eyes on the Solar System has a simple mode and an advanced mode. The simple mode is for everybody over age 30. That's the simple mode. The advanced mode is for the rest of us. I'm going to start by showing you the advanced mode to give you an idea of context. One of the important things to do is to make sure that you go full screen. And we remind you, there's a toggle here, allows you to go full screen. And then we provide for you a virtual camera. It looks a lot like a mouse, but actually it's your camera, and just by clicking and dragging somewhere in space, you can change that camera's viewpoint. And then to change the center of your field of view, you just double-click on a label. So I'm just going to double-click on Mars to show you. We will then fly to Mars, we'll download the data, and all of the satellites that you see here and celestial objects are in their correct location. We preserve scale and distance. So I'm going to zoom back here a ways. I'm going to keep zooming out, and we're going to look for New Horizons. And there it is. It's out past Neptune. So if I double-click on a spacecraft, we will then travel New Horizons. So there it is, spinning at its proper rate, pointing back its antenna back at the Earth, and Pluto is in the distance. Now, I could spend a great deal of time showing you all the various controls at the bottom. Don't have that much time. I'm going to let you do that on your own. What I'm going to show you is something we built called Eyes on Pluto that gives you an opportunity to set up the user interface in a way specific to this particular mission. So under Tours and Features, you click the feature called New Horizons, and then what's taking place is we are loading a special user interface that's all about the New Horizons in closest approach to Pluto. It says computer simulation at the top and live. That means that that is where where New Horizons is right now relative to Pluto. We list data like that's your distance to Pluto, its relative speed to Pluto, its closest approach time, 37 days, 17 hours, 25 minutes. And then notice on the right-hand side you have the current time, so that's right now. There are two modes. We're in the live mode. There's also a preview mode. Before I go to preview mode, I want to show you the camera modes. We're in ride-along mode, which means we are riding along with the spacecraft and the camera's locked on Pluto. So if I click and drag, Pluto always stays in the field of view. If I click the spacecraft camera, the focus is on New Horizons, so I can turn and look at all the different instruments, rotate around, go back to the Earth, look wherever I want. And then I'll get to the overview when I move to the preview mode. So I'm going to leave that camera for the preview mode, and I'm going to go ahead and click preview. What preview will do, it takes you 1 day from the event. I'm going to go to ride along. And now you are looking at what's going to take place on the day, July 13th at 10 a.m. And when you see those colored lines projecting from the spacecraft, those are the field of view lines for the various instruments. So I'm going to speed up time here. It's at 10 minutes a second now. So this is the sequence we were given by our colleagues here at APL. This is what it's going to be doing at the time indicated. So if you travel to, if you come to the software at this, on that morning, I'm going to go ahead and pause it when it gets about 50,000 miles away. And I'm going to go I'll go at about 30 seconds a second. So you can see that the spacecraft is very, very active during this period. You can see where it's located. This window here shows you the instruments that are turned on. So for example, let me slow it down one notch. You can see that Lori, Ralph, and Alice are all powered up, which means they could be taking data. The field of view line for Lori shows you that's a 1,000 by 1,000 image. I have a minute. So there's another feature. You can roll over each of these instrument names, and we will tell you what those instruments do. So this tool, NASA's Eyes, allows you to be that armchair explorer. Now I promised I'd show you the spacecraft view, excuse me, the overview. So if you hit overview, it shows you where the spacecraft is relative to the system. And again, on July 14th at 7 in the morning, it's still coming in. All right, so I will pause now for any questions that may be either in the room or elsewhere.
We have time for just one quick question. Any questions? All right.
Is this all open source, or is...
The software is not open source, but it is available to anybody on a Windows or Macintosh computer to operate in this fashion.
All right, wonderful. So hopefully you guys will go and download Eyes on the Solar System here in order to follow along during the flyby. To get more information about the mission as the flyby is happening and everything leading up to the flyby, you can visit the NASA website at www.nasa.gov/New Horizons. Be sure to follow along with the mission on @NASA New Horizons on Twitter. And be sure to follow along with everything that NASA has going on social media. Thank you all for joining us today for the NASA Social. We're getting really excited. July 14th is coming, Pluto's coming, and we hope to get some of the best results we've ever had and take a look at a whole new perspective on Pluto here. So thanks for joining us for today's NASA Social. Go New Horizons.